All right, so good morning, everyone. Just to reiterate our moderator's introduction, my name is Felipe Sanchez. I'm a PhD candidate at the Center for Geospatial Analytics at North Carolina State University. And I kind of live in this weird middle ground between epidemiologist and kind of GIS person. So every time I come to these conferences, it's kind of like very surprising because so many things people are doing with GIS that are like not within my wheelhouse. So it's nice to see that. I've been living in this epi bubble for so long, but anyway, this is work that I've been doing for chapter 2 of my dissertation, using deep learning and aerial imagery to predict swine farms across the United States, and we'll get to why that's important. But first, I'd like to thank NC State, the Center for Geospatial Analytics, and the College of Veterinary Medicine for support for this project. So at my lab, we build these spatial epidemiological models for livestock animals. And it's not exclusive to epidemiology that when you're trying to kind of build these models, you rely on good data. And so these models are essential for quantifying farm-to-farm transmission dynamics, understanding disease transmission pathways, so the movement of infected animals from farms to farms, contaminated trucks, contaminated personnel, and airborne viral particle dispersal. And it's also useful for estimating disease control and eradication strategies, so establishing movement standstills and perimeters around infected farms to kind of just control the outbreaks. But what I was mentioning is that we often have like incomplete data to work with, and specifically for epidemiological models, we need kind of the precise farm location data to kind of build our disease spread models. And also demographic data such as how big is the population and what production type is this specific farm, because different production types, whether if it's a breeder farm or a finishing farm or something like that, they have different transmission dynamics. So often this data is missing or kind of confidential, and it's not publicly available. So we're kind of limited on the data that we have to build these spatial epidemiological models. And when we don't have this data, we're left kind of making assumptions of the data. So we're left doing spatial distributions of random distribution of farms and estimating or simulating the size and production types of these farms. And when we do this, we kind of inherently integrate uncertainty into our models, and that can under or overestimate the transmission rates and limit our interpretation of kind of disease dynamics and outbreak predictions. So to kind of address this, we want to detect swine farms across the US using high-resolution aerial imagery. Once we detect them, we want to classify them into one of the 4 kind of major production types, which is sow, finisher, nursery, and boar stud. And then once we have that information, we want to predict the population size based on information that we've already gathered in our kind of data set. So how we did do this, we built this machine learning workflow where we have a deep learning semantic segmentation model that first finds the barns, and then we have a random forest classifier and a random forest regression model that classifies the barns into their 4 corresponding production types, and then we estimate the population size for these, and we kind of run this for the entire US, and we get the entire US population. And so I'll go one by one and kind of go through the entire workflow. So starting with the input data sets. So we used high resolution aerial imagery from the National Agricultural Imagery Program, or better known as NAEP. It has a spatial resolution of 0.3 or 0.6 meters. We kind of converted them to zero point 0.6 meters, so we had kind of even spatial resolution across the entire United States. And then we used polygons of barns from RabApp. So the Rapid Access Biosecurity app is an app that we're building in our lab. It provides swine producers and other kind of livestock producers biosecurity information that helps with being prepared for outbreaks and establishing what farms are at risk and potential for outbreaks. And we provide this to the producers so they're well prepared. And so within that process, we collect information from them. And among the things that we collect from them are maps of the premises, which we digitize. And then we have all these biosecurity features in that kind of left box column for the farms. And so kind of using that information, I create masks, raster masks for our tiles that we get from all the counties. So we download the nape imagery as compressed county mosaics, chop them up into 512 by 512 meter tiles, and overlay it with the polygons of the barns and create a mask. So we have 15,841 barns. And so that is what kind of goes as input into our semantic segmentation model. And so just to reiterate, we have our 512 by 512 meter tiles that we chopped up for all the counties and their corresponding masks. We split that data into 70% training, 10% validation, and 20% testing. And we input that into our model, which has a unit architecture. It's kind of a widely used deep learning model for segmentation or building footprint extraction. But we used a ResNet encoder backbone that is kind of a model that's been trained before on the ImageNet data set, which is a huge data set of different features. And you kind of include this model as a pre-learned model for different features. So it kind of helps the model already distinguish kind of buildings and stuff like that. And the last layer of the unit model is the softmax layer, which provides pixel probabilities predictions for each of our tiles. So it'll go from 0 to 1 on the probability of it being a barn or a background. And then we evaluate our model using mean intersection over union. So intersection over union is basically how well the prediction overlaps with your ground truth label. And then the F2 score, which is a kind of a mean between precision and recall, but with a little bit more emphasis in recall, because for this specific kind of task, it's more important to detect the false negatives and rather than have better precision. So we want to be able to we don't care if the model predicts wrong, we just want to find everything available. So there's more importance going into recall. So just going into the results. Pretty excited on the performance of our model so far. So we had a mean IOU of 0.93 for our training and then 0.92 for our validation, and an F2 score of 0.94 for both our training and validation data set, which is very promising. We trained this model for 100 epochs. Epochs are just kind of iterations of the same data set. And it had an early stop, so I put in so it doesn't unnecessarily train the model and overfit the model. I had an early stopping when it kind of converges. And so it stopped at 40, and that's kind of the number of epochs it trained for. But yeah, very promising results, and we kind of look at some of the results. So these are some mosaic tiles of some kind of examples of our predictions. So you can see, it's kind of hard to see, but yeah, those red squares represent kind of swine barns, and you can see on the right we have our predictions. And so basically we're running all of this data and kind of finding swine barns, and goes from 0 to 1 being the bright yellow ones with high predictions for swine barns. So yeah, we're very excited with kind of this product. Um, on occasions, the model will get confused, understandably, because we're relying on kind of the reflectance values from the farms and kind of learning from the different features that the model considers important to distinguish a barn from a non-barn. So the model will get confused, and sometimes these like kind of ghostly kind of figures appear right there, which is kind of the model allotting a little bit of probability to these pixels, saying maybe it's a barn or maybe it's not. But that's kind of when the next part of the workflow comes in, which is the feature filtering. And so what we do is we kind of calculated basic descriptive statistics for all of our barns. So what is the mean area and the standard deviation of the area of a regular swine barn? What's the aspect ratio and length and width, that type of stuff. And we use that information to filter out all of the kind of predictions that fall outside of that range. And so by doing that, we take those kind of little ghostly figures that kind of are smaller or kind of smaller prediction, and we basically just kind of exclude them. And so we're left with a really clean data set of swine barns. Next, moving on to the random forest classifier. So as I mentioned, we want to take these predictions and classify them into one of the 4 production types. And so how we did this, we took information, metadata from kind of our existing data set of swine farms and calculated a bunch of different kind of descriptive statistics, and we input that into our random forest classifier. And yeah, it performed pretty well. It predicted pretty well for, obviously, for kind of the majority of the class of boar studs. There's really not a lot of boar studs in our data set, so it's a really rare class. So obviously it will perform poorly, but our 3 major kind of swine farms, so Finisher, Nursery, and Sow, they performed pretty well. So we're pretty happy with the precision and the recall for a random forest classifier. And so once we classified our data set, we move on to kind of the population size estimates. So we used a random forest regression, and so our square score was 0.78, which is it's pretty good. It's reasonable for kind of just estimating the population size of these predicted swine farms across the U.S. So while it's not a great R2 score, our square score, most of the data that we have fall within the RMSE confidence intervals. So 87% of our data falls within those confidence intervals. So we feel pretty confident that it's actually doing a good job at predicting the population size, except for when we get to these kind of values over here, which are kind of our very, very big farms, that it's a little harder for the model to kind of be able to predict those values, because it's just such a large barn that it really doesn't know how to estimate the amount of animals that are in those barns. So we kind of analyzed the data a little bit more, and kind of just to assess the deviation of the model. And so we found that the model, within 500 pigs, our data fell within, or 63% of our data fell within estimates of 500 pigs, 75 of 1,000 pigs, and 2,000 87%. So it's performing pretty well. It's only kind of deviating as much as 2,000 pigs, which in the grand scheme of things is very little compared to the amount of pigs that there are in, talking about millions and millions of pigs in the United States. So we're pretty happy with the results, and only 2% fell outside that range of 5,000 pigs. So we're still kind of tweaking this model a little bit. There's potential for improvements, but overall we're pretty kind of content with the results. And then our next step is, well, that's the kind of just letting it run part and just predicting it for the entire U.S., which will take a lot of time, or a lot of computing power, I should say, not necessarily time, but yeah. leaning on the high performance computers at, at NC State for this. But other than that, I'm open to some questions. Thank you for your time. Oh. Yeah.
Does the study take into consideration wild pigs?
No. So this is only commercial swine farms. Yeah. Yes.
This seems like the perfect use case for nuclear engines. Did you try that?
Yeah. So we kind of, as far as obtaining the nape imagery, you mean, or?
The whole process.
Yeah, I can look into that. Yeah, sure.
Excuse me. Is the model able to like successfully distinguish between other large agricultural production facilities like poultry, and like when you expand to the whole U.S., do you use any like breakdown of production at like say the county level or whatever, where North Carolina, like a large barn that may have a similar aspect ratio, so it might more likely be a swine operation versus central Pennsylvania where it's more likely poultry or something.
Yeah, that's a great question, and we typically see some false positives with other farm types, specifically poultry, because they look so similar. But I was pleasantly surprised that it usually, while it did predict or false positives for the poultry bones, it usually was kind of lower probabilities. So we're able to kind of filter those out a little bit. But yes, that is definitely a problem. And as far as the geographical differences that you were mentioning, we trained our model with farms from all across the United States that are in RABAP. So RABAP has 22 states of the pig production regions, big production like the Midwest, the East, and kind of Texas and that area. We have plenty of training data to kind of cover the differences between the barns. Yes.
I'm curious about like ghost images.
Mm-hmm.
So it looked like those were near real barns.
Mm-hmm.
Is that typically like they're near them, they're not just like by themselves?
Yeah, it's usually just offices or kind of or little storages that they have near the barn. So it's saying, okay, this structure looks kind of like a barn, but it's not the shape. So I'm gonna give it a little bit of probability that it is a barn, but it's not entirely sure. I'm speaking in model lingo, but yeah, that's what the ghost images are. It's just kind of confusion between, it's not entirely sure it's a barn or another building, and so that's kind of.
For the question about being used in poultry
Mm-hmm.
units, do you filter by like whether or not there's a
Yeah, that's a useful thing to kind of consider for the East Coast, but the East Coast is unique that it has lagoons. All swine farms don't have lagoons. So, yeah. Yeah.
Do you find that the model is more or less predictive with like larger scale factory farms versus like smaller family operations?
Yeah, that's also a good point. This is just strictly commercial swine farms. It's not backyard kind of operations. So it'd be great if we could find that, but yeah, I don't think we're quite there as far as detecting that. Yes. Yeah.
So you're looking for rectangular shiny objects, right? That's basically.
Essentially, yeah.
How do you what in your model do you think is helping it differentiate a CAFO for swine versus a CAFO? What about that is it training on? Do you think differentiates the two sectors?
Yeah, it's. I haven't quite delved into the different kind of layers of the unit model to kind of figure out what actual parameters are helping in distinguishing kind of a swine farm from a poultry barn. But it definitely takes into consideration kind of the surrounding areas. That's why we decided on 512 by 512 instead of 256 by 256, which is another valid input for a unit model. We felt that 512 meters provided a more kind of representation of what a swine farm looks like, and allows the model to have more kind of contextual information on learning. Okay, it has these like roadways that go around it, and it usually has these line of trees around it, and lagoons and that type of stuff. So I was pleasantly surprised how well it was able to distinguish swine farms from other different kind of ag farms. And yes, in the back. So just to kind of reiterate your question, you're asking if some of the barns are active or not active? Yeah. So it does not take into consideration whether it's active or not active. Our data set includes active and non-active farm because the target of the model is to just find them at this point, not necessarily determining if they're active or not active. Yeah, that's important consideration, and that's why we use kind of the latest collection of NAPE imagery, so 2022 and 2023 for some states, because it kind of staggers between the states, to ensure that we have the latest kind of visual of a barn, and we don't expect a lot of differences as far as structures goes from 2023 to now. Yeah. Yes, in the back. No, that is all confidential information, and so that's kind of one of the limitations to other kind of researchers and people that want to pursue kind of this. They want to see or want to know where the swine farms are, so they can build these epidemiological models. But that information is not readily available, and so once I finish this project and this data I generate all this data, I can't share with anyone, but what I can share is the model and model weights. So all of that will be open source, and you can take my model that has been trained on this expansive data set of swine farms and apply it to your imagery, and voila, you got predictions. Yeah.
My question is towards the deep learning model.
Yeah.
Have we explored the more scalable architectures as we, when you went to the entire state?
Mm-hmm.
Right. So,
Like which one?
was there any difference in the accuracy analysis?
So I explored using EfficientNet instead of ResNet or UNet, which is another kind of typical architecture for semantic segmentation of buildings specifically. And I also tested different kind of versions of ResNet. I did 128 and 32 and kind of different depths to the ResNet model. And I found 50, and this configuration of UNet ResNet 50 specifically worked the best and produced the best results compared to the other models that I tested. Yeah.
Just shooting at the wall because I'm not sure exactly what, but would there be any benefit to like fitting the R2 line to each different type of pig farm? For the nursery or for the finisher?
Yeah, absolutely. Yeah, I'm sure there is different kind of fit to the different production types, but I kind of was just kind of exploring the entire data set, which is kind of what I'm looking at. Good question.
Other questions? Nope, no more
All right.
questions? And let's give
Thank you.